All right, let's go ahead and get started. I'm Mike Human, and this is the G2M Research Multi-Vendor webinar on best practices for deploying NVMe over fabrics. Joining us are Dave Montgomery from Western Digital, Joel Detrick from Kioxia, Rob Davis from Mellanox, from Xilinx we've got Tom Spencer, and from Accelero we've got Josh Goldenhar. So let me go through some of the agenda real quick and some of the ground rules. So as you see, this webinar should take about an hour and 20 minutes. Please, for questions that you have, submit them through the Q&A window on Zoom. We'll answer all the questions at the end of the session. That would be the best way to do it. We're also recording this webinar, so we will send a link to the recording and a copy of the slides in PDF format to everybody who's registered, so you'll get to do that. One other thing we have is we'll have a couple audience surveys. There's 2 of them in here that we'll do in between the panel questions that we're going to do after the vendor presentations. So just use your webinar, your Zoom control to respond to the polls when they pop up on your screen. And with that, let's go ahead and get started. So I'll kind of do a first introduction. So we talked a little bit. We have Rob Davis from Mellanox, Tom Spencer, Senior Product Marketing Manager from Xilinx, Dave Montgomery, who's Director of Data Center Systems from Western Digital, Josh Goldenhar, who's VP of Products at Accelero, Joel Detrick, who is VP and GM of Network Storage Software at Kioxia, and then I'm Mike Human. I'm the Managing Partner of G2M Research. So quick kind of intro for me. One of the questions we always hear is, what is NVMe over fabrics? I think everybody understands the concept. It's really a way of taking the NVMe interface and remoting it to computers over a variety of different protocols and transports. In Ethernet, we've got at least 3 flavors of it. We've got NVMe TCP, NVMe over ARCI, NVMe over iWarp. In Fiber Channel, there's NVMe over Fiber Channel, and in InfiniBand, there's an NVMe over InfiniBand. The great thing about NVMe over fabrics is you can get near local SSD performance across a network, and that happens in NVMe over fabrics because it really eliminates a lot of the overhead that's been associated with the network SCSI protocols, such as iSCSI, FCP, or things like that have really added additional latency to SCSI. So we're going to talk a little bit about some different use cases in here. There's 3 I think they're of primary interest. One is called scale-out flash storage. This is a use case where you have a bunch of servers and or storage appliances with NVMe SSDs in each of them, and you use a software package to make this look like a single namespace. So it's kind of like DAS in the sense that each device or each server has its own devices, but that they're shared globally, so they can also be managed globally. The second one, and this one we've seen a lot of adoption over the past couple of years, is using NVMe over fabrics as a backend for all flash arrays. Previously, using say SAS or SATA protocols, you typically had a 2-to-1 relationship between controllers and JBOFs within the back end of an array. That kind of limited the things you could do for availability and for fall behind. With NVMe over fabric, you can actually implement a true fabric in the back end of an array. That allows a lot more flexibility. Concepts like software-defined storage become possible. So that's one of the reasons that's become very popular. And then on literally the flip side of that is the classical storage initiated target use case where you have a target, whether it's a JBOF, whether it's an all-flash array, whether it's a scale flash storage node, talking to an initiator, a server that doesn't have storage, and it's doing all of the storage traffic over the network. So with that, let's go ahead and get to the presentations. We'll start out with Rob from Mellanox. Rob, I'm going to pass you control. You should be able to control the screen now.
Thank you very much for the opportunity to be on this webcast. So I'm trying to change the screen. So Mike, sorry, it's not changing for me.
Let me see here what we can do. Okay, let me try passing it to you again. All right, you should be able to just move your mouse around. It should take over.
Okay.
There we go.
Perfect. Thank you. Sorry for that. So first, it's important to realize that NVMe over Fabric's best practices are both use case and application dependent. And I'm going to focus on the use cases that Mike talked about, since there's also storage application suppliers on this panel that I'm sure are going to cover the application from the use case perspective. So let's start with the scale-out storage and focus on the DAS-like performance requirement there that Mike talked about. If we look at DAS performance on bandwidth of NVMe SSDs and compare it to Ethernet speeds, we can see right away that to achieve the DAS-like performance, we need at least 25 gigabits. And if we want more than one SSD, then we need 50 gig or greater. So for best practices where DAS-like performance on bandwidth is needed, you probably want to actually go with 100 gig, because in many cases you've got at least 4 SSDs on your storage nodes. And also in these use cases, best practice is probably not going to be able to support fiber channel, because the fiber channel speed is really not an option unless you have very few SSDs. Bandwidth isn't important. Another use case not mentioned by Mike is compute storage disaggregation. It has other names as well, but what happens here is you remove the storage from the compute to get efficiency. This is something the cloud vendors are looking at or implementing now quite a bit. And because of that, because you've converted from DAS to network storage, NVMe over Fabrics is perfect as long as you can maintain that performance. So for best practices here, again, you need very high bandwidth, at least 100 or multiple hundreds or 200 gig, because that whole rack of servers is now accessing the DAS through the storage in the rack or the storage down the row. We also see this application a lot with cloud customers, especially ones that are using our SoCs, our Bluefield SoC. So the other important aspect of the DAS performance, maintaining DAS performance, is latency. So here you can see a chart that shows comparing the switch and adapter latency to NVMe SSDs. And the new NVMe SSDs are actually, there's 1 micron just announced, I think, that's around 3 microseconds. So this is very important. And there's actually vendors like Mellanox that have very low latency switches and adapters. And if you use our DMA protocol, then you're able to maintain that with a protocol that also matches low latency. Because most networks have multiple hops, like you're going down the row, then you've got a top of rack switch and an end of row switch, this latency gets multiplied. Also, NVMe over Fabrics is a request response protocol. So you actually have to double it. So you have to count your hops, and then you have to double it. And then you have to worry about things like store and forward. Some switches handle store and forward differently. Mellanox switches have adaptive store and forward, so they don't add latency by storing the entire data packet before they move it, because you've got a speed mismatch. So best practices for the latency side of getting DAS performance out of NVMe over Fabrics is to use our DMA protocol and very low latency switches and adapters. The next use case that Mike talked about was all-flash array backend. And this use case is really good to use as an example when talking about congestion control, which is another best practices area for NVMe over Fabrics. And that's because, as Mike's diagram shows, you scale both the front-end controllers and you scale the JBOFs, or all-flash array components, on the back end. And this creates a lot of congestion. Getting congestion control right is really important to keep that DAS-like performance, and there's different ways of doing it. So there's global pause, which is standardized by IEEE. There's priority flow control, which is also IEEE, and it allows you to add multiple levels of priority. There's ECN, which is kind of a combination of switch and adapters. That comes from the IETF. And then there's a DC QCN, which is a flow control method used by Rocky. All of them are actually can be used by Rocky or any of the Ethernet-based NVMe over Fabric protocols. And it's important to get this right, and here's an example. So here's an example of ECN, which isn't quite right, and you can see that it's working and that it's keeping congestion from dropping packets, but it's also doing a lot of starts and stops, kind of like traffic during rush hour. And so it's not very efficient. You're losing bandwidth and latency because it isn't set up correctly. And here you can see ECN that has been set up correctly, and the switch is well designed to handle it, and you're getting no pauses, so you're maintaining your latency and your bandwidth. So the best practices on congestion is to make sure your switches and adapters have really good congestion control. And the last use case that Mike talked about was classic storage initiator and target. I like to call this classic SAN. This is where Fiber Channel and iSCSI played for years, but with NVMe over Fabrics, the bandwidth and latency can get a major boost. NVMe over TCP is a really good fit here, and you can of course use Rocky as well. But you need to be aware of one thing when you're working with NVMe over TCP, and that's tail latency. Tail latency is important for many applications, and you can here's a white paper that talks about those. So from a best practices perspective, you want to make sure if you're using NVMe over TCP that you're aware of tail latency and whatever, and that's acceptable to the application. Now, don't get me wrong, Mellanox supports NVMe over TCP across all our products, and it fits many use cases very well. You just have to be aware of the tail latency. So on this chart, you can see the local performance in the brown for the writes and the local read performance in the purple, and you see that the RDMA tracks very closely with a little added network latency to the SSDs, but because of the kernel and the way TCP handles congestion in the network, you can get a lot of tail latency once you get up into the high percentages, and that causes the disconnect. And then finally, one last thing is security. So when NVMe over Fabrics is Ethernet based, when you think of SANs that were fiber channel based, you basically had a way of isolating the fiber channel SAN from the security concerns of the Ethernet, which is more easily compromised. But now with NVMe over Fabrics, of course, we have a network that's can be all Ethernet based in the Rocky or the NVMe over TCP situations. And you got to be careful, because the obvious solution is you can encrypt the data as it crosses the network, but that encryption can cause a lot of latency and bandwidth restrictions if it's software based. So the best practices here is to make sure that you use encryption offloads to maintain your NVMe over Fabrics performance. And Mellanox just announced the ConnectX-6 DX, which has that incorporated into the RNIC. And that's my 5 minutes, Mike.
Perfect. Thanks, Rob. If you could pass me control again, I might be able to see if I can get it actually. There we go. I've got it now. Okay. So next is Tom Spencer. Tom's with Xilinx. Tom, let me pass you remote control. Or you should have it now, so you can go ahead and flip the slides.
Okay. All right. Thanks a lot, Mike. So it's going to let me go. There it goes. Okay. Sorry. User error. All right. Thanks a lot, Mike. So starting out with looking at the market for SSDs, I think it's pretty much understood that SSDs are the predominant technology for storage versus spinning hard drives. And if you look on the chart on the left, the PCI Express interface, which is really the root of NVMe-oF, Some early solutions on NVMe-oF were doing translation to SCSI using old transports. Today, PCI Express over the various interfaces that you highlighted at the beginning of the presentation are the dominant transport. So if you look at some of the performance aspects, you know, where we are today, we're somewhere in between the third and fourth panel on this slide here. And you've got PCI Express Gen 3, very soon moving to PCI Express Gen 4, 1.5 million IOPS up to 3 million IOPS. And if you look at the latency characteristics, 20 to 40 microseconds today, moving quickly to the sub 10 microsecond latencies. So we've already seen early benchmarks with things like 3D Crosspoint. In fact, we've got a slide on here where we're displaying some performance numbers using one of those drives. So if I look at the modern cloud infrastructure, this is a depiction of a standard depiction of a cloud infrastructure. You've got your CDN on the front, you've got your web tier, your application tier, and your backend storage. And the use cases that you and Rob have already highlighted, you've got distributed or disaggregated storage, which can be running in any of the web or application tiers. And then in the back end, you can be running all flash arrays or JBOFs. And there are different variations within these tiers, but these are the different locations where one might be running NVMe-oF. When we get to the benchmark numbers and some of the numbers that Rob was showing, and you had highlighted this too, Mike, you can now get with NVMe-oF very near direct attached storage performance numbers with TCP, with Rocky, with the different transports. And these numbers are orders of magnitude faster than traditional network storage. So I believe that NVMe-oF together with SSDs is going to move a lot quicker for network storage than we saw previously with things like Fiber Channel and iSCSI. Some of the benchmark numbers. So I've got two sets of benchmark numbers here. This is standard TCP using a kernel device driver. So this is what you'll find that was pushed upstream to the Linux community, what was accepted in the consortium. There's basically a plugin that any adapter card can use with a standard NIC, so it doesn't matter which supplier it is. And you'll basically be able to map the NVMe commands into TCP. And so what we did here, if you look at any one of these three diagrams, we're looking at both IOPS, which is on the left. We're looking at latency, both write and read on the right-hand side. And the comparisons that we ran were, we did direct attached storage, which was highlighted in blue, one of the blue colors, I should say. Then we ran kernel plugin on the SolarFlare adapter, now owned by Xilinx. We ran it on a competitor's NIC, and then we ran Rocky on a competitor's NIC, and then we ran iSCSI just for grins. You can see the iSCSI is completely off the charts. It's not even close to the performance that you're going to see with the NVMe-oF, traditional NVMe-oF. Over here, the iSCSI goes off the charts this direction with latency, but there's a very tight coupling of TCP and Rocky, whether it's on our adapter card or somebody else's. And so this is what you can get with the standard Linux plugin. Now, some of the things that were pointed out with the tail latency, with TCP, this is all born, not all, a lot of it is born in the OS, in the operating system. So if you look at context switching in the operating system, and think about a target device where you've got lots of initiators banging on a target device, you're going to have lots of flows going in and out of that target device, and you're going to have the operating system managing all those flows. If you go with a user space solution, so before we can get to the networking, what we're highlighting here is SPDK, I believe most of you are familiar with. This is a user space solution where you're bypassing the operating system, going straight to the SSD. So this exists today. And what you end up doing is you bypass all of this congestion in the operating system, in the kernel. So in a similar fashion, what we did is we took our kernel bypass technology, it's called onload. We coupled that with SPDK. So now you've got direct writes and reads to the drive, and you have direct access to the network all through user space. And what you end up doing is bypassing all that congestion. With that, so here's a depiction of it. So you come in off the network through the adapter into user space, and then through the user space through SPDK to the SSDs. What we were able to demonstrate, what you see here on this chart on the very bottom, if you look in the bottom left, you see the Intel Optane direct attached storage is approximately 10 microseconds. And by bypassing the kernel, so here's your Linux kernel solution, sitting up here around 37, 38 microseconds, whatever that number is. Just running SPDK, so going through a Linux kernel off the network into SPDK, you drop the latency by 35%, and then bypassing the kernel completely, coming through onload, straight to SPDK, back to the SSDs, 54% drop in latency. And so this is something that we were able to demonstrate on a 100 gig adapter using our onload technology combined with SPDK. So some of the, I don't even want to call them limitations, but you can enhance the performance of TCP. We're getting numbers upwards of 40% better than a kernel solution. And what we're focused on is using that technology on the target side only. That's where we think it's most applicable. So in summary, we do believe TCP will be predominantly used in cloud infrastructure. Certainly there are other solutions out there and good solutions out there. Why would TCP be the predominant choice? It's ubiquitous. It allows legacy infrastructure to be used, so there's no upgrade of infrastructure. Using kernel bypass, we can get past some of the potential issues that were, Rob had flagged a few of those, and we can get better performance in general. We do have a long-term strategy for NVMe-oF solutions, and today we're currently working with multiple partners. We invite other partners to collaborate with us, and certainly for the end users, we are available anytime. Let us know if you're interested in looking at a demo or an evaluation, and I'll pass the baton back over to the next speaker.
Thanks a lot, Tom. And we will now have Dave Montgomery. Dave is with Western Digital, and Dave, I'm going to give you control here. You should be ready to go.
A little bit of background. Dave Montgomery, I've been at Western Digital via the SanDisk acquisition for about 7 years. Prior to that, NetApp. Prior to that, HP Enterprise. And so my background is very much in storage systems and large Unix systems, both in networking and operating systems. So I very much agree with everything my colleagues on the panel have said going to this point. Western Digital, to state the obvious, is a storage company, and we're staying with storage. We're not going to become an applications or networking or compute vendor or anything else. One of the things we feel NVMe over Fabric enables is this vision of a composable infrastructure in which you've got lots of resources, and you see them sort of tiled out at the bottom, whether it's flash, disk, memory, FPGA, and you are able to use them on demand and then relinquish them when you're done with them. And so clearly we're starting with flash because that's a high cost asset that lots of workloads need a lot of flash for a relatively short period of time. And currently it's rather cumbersome to try to do that without sinking a lot of money into flash that doesn't get used very frequently. So from a Western Digital point of view, what we want to do is basically have NVMe over Fabric become the interconnect for all these hardware resources. And so just like, if you go back 15 plus years ago, VMware virtualized CPUs. And so you didn't really care where your CPU was as long as it had enough or as long as it had enough processing power to get your workload done. And then when you were done, it could be moved somewhere else or downscaled or whatever. So that exact concept we feel is going to sort of start encroaching on or start being used in IT infrastructure, beginning with the high-priced assets like flash and GPUs, CPUs, et cetera. So there's it's kind of an extension of the virtualization trend that began about 15 plus years ago with VMware. Here's kind of a couple of examples that might help put this into perspective. We've got a bunch of virtualized resources, and you can see, I'm not going to read the labels, you can read them as well as I can. So the first workload needs a little bit of CPU, a little bit of GPU, more memory, and a little bit of flash. Doesn't really need much else than that. So that workload gets those resources, starts running, completes its work, and then the next one needs, again, a little bit of CPU cores, a lot of DRAM. So you can see in the memory thing that this workload now needs a lot of memory. It needs flash and some disk as well. So that workload kicks off, concludes. You then have a third workload, which needs really just CPUs and disk, a little bit of memory. And that's, we can all think of a workload like backup, archive, something like that would require a lot of disk, tiny bit of memory, tiny bit of CPU. And then finally, you've got your fourth workload, which really needs an FPGA, like a Xilinx storage coprocessor. And we were actually working with Xilinx on that. And it needs a fair amount of memory and a fair amount of flash, whether it's an analytics workload or a specialized GPU-centric kind of task. So by having a fabric attach all this, and the panelists before me extolled the reality and the virtues of low latency, high bandwidth, high throughput of NVMe over Fabric, you're able to get the most out of lots of high cost assets. Now, Western Digital has a series of products we introduced about 18 months ago. It's a flash device with 10 blades in it. We've submitted the hardware architecture and the software architecture to numerous standards bodies. We're working with several of my panelists' companies to enhance this and integrate with their products. There's a management dashboard that you can use to control how you assign flash and how much or how little that flash, how size of flash. So this is it's a great way to use a high-cost resource, similar to what I think when the earlier speaker said we recommend 50 to 100 gig Ethernet. The current version we've been shipping supports Rocky V2, so it's RDMA. We will be coming out very soon with a TCP version of it, but it's available today. And so this is, as I said a few slides back, we view NVMe over Fabric as a really attractive on-ramp to this composable world. And so these are our product offerings. Latencies, 34 microseconds. Bandwidth is 20 gigabytes per second out the back end. So it really is, as one of my co-presenters said, it's like DAS storage over the network. It gives you a huge amount of performance. And then finally, to get started, we have up and running for 6 months now a lab in Colorado Springs to help people work on NVMe over Fabric using not only our products, but a lot of our partners' products. Let me get rid of that. And so that's it for me. Let me turn it over to Accelero, another partner of Western Digital's, but that's it. So Mike, you can grab the ball, or if I need to relinquish control, let me know.
Sure thing. So Josh, let me pass you control here real quick, and we'll let you get started. There we go.
Thanks, Mike. All right, so you've heard a lot, and I can't say that I disagree with anybody on the call today. If you are still there and you're still awake, congratulations. I am lucky enough to be the fourth and last presenter. So what you've really seen in our day and age, and what is evidenced by the other folks here we're presenting is this culmination of all these different technologies at the same time that are really making NVMe over Fabric a reality, something that, as was said earlier, we think will be adopted much faster than normal because everything is just in place. If you look at the software needs in the AI space for compute, we've got huge advances, especially around GPUs and AI. In a container environment now, it's very common practice to use Kubernetes. Of course, this is on top of GPUs, ARM, even Power is here, Intel, AMD making great strides, and in fact coming out in the x86 space with PCIe Gen 4, which of course then enables the cards from at least Mellanox, the ones I know of, that are PCIe Gen 4, and now we can actually get 200 gigabit out of a single by 16 slot. So we've really seen these huge advances. And when you put all these things together, it basically paints this picture that you can disaggregate storage. And furthermore, as we've heard from Western Digital, you can also go for a composable infrastructure. Although there's one big piece that has not been talked about, which is we really view as missing, is if you look at all these pieces, they are just that. They're piece parts. And the question is, if you were to densely populate your network with NVMe over Fabric devices, what you end up with is a network that's full of individual, maybe tens, maybe hundreds, maybe thousands of individual drives, all available on the network. And what do you do with those? The question is, how do you change from looking at drives to being storage? Especially the reason to do this is strong, is that you want to go ahead and take advantage of the unprecedented performance you can get. I am happy to say that Kioxia is a partner, but there are drives that have come out recently on the market that in a by 16 slot can do over 9 gigabytes per second, up to 2.5 million IOPS with ultra low latency, as low as 8 microseconds. I believe that was announced by Micron for their Optane or like product. So these are game changing. And when you put boxes of flash, you have tens of millions of IOPS available and massive amounts of bandwidth. So you absolutely positively want to and have to share. But the question is why, and that should be obvious. You want to take advantage of that IOPS and bandwidth utilization. I would submit to you that when you have 2 or 3 drives that can do a couple of million of IOPS, you will be at a disadvantage in actually utilizing those IOPS in any one host. This is the reason to share. We can do this with benchmarks, but when you run an actual application, it's very, very difficult to consume over 1 million or 1.5 million IOPS per CPU socket. You just get into issues with the way applications are written that you can't use those. So you want to share. This is the reason to move everything out. And as was mentioned multiple times, you get local latency now. So why not? Why not move it outside? This means you have the freedom of choosing the kind of application server platform you want. You don't have to have U.2 slots. You don't have to have PCIe slots. Your compute blades or systems can be very, very dense. All they have to have is a network interface. But now you get to the point that, well, okay, so I have all these drives out there. The individual drives work just like local storage, the same latency, and if you have enough adapters and enough bandwidth in your adapters, you get the same bandwidth as well. So now what you have in this scenario is what I like to call remote DAS. And I know that's somewhat of a misnomer, but it's on purpose. You have essentially direct attached storage, but it's remote. And those two things together can actually kind of cause headaches. You need a management layer. You need protection against failures of not just drives, but also of chassis. And so that's what is the missing piece. And I would submit to you that that missing piece is filled by Accelero NVMesh. What we call elastic NVMe is you can use NVMe over Fabric, or you can use the native NVMesh API or protocols, and we virtualize all that NVMe flash. So as was mentioned earlier, just like VMware long ago really virtualized out CPUs and got you the highest utilization rates of those CPUs, that's what NVMesh does for NVMe over Fabric. You can have all these drives with all their available capabilities, and we virtualize those out, giving you logical volumes, giving you the ability to have failover of both drives and hosts. It makes this large elastic pool of NVMe get offered up as basically virtual NVMe devices. And in this way, you can go to data center scale. You can feed things like GPUs with local speeds and enable full virtualization. And in fact, you can get higher bandwidth out through network interfaces on systems like DGX1 and DGX2. You can get higher bandwidth out the Rocky interfaces than you can from local NVMe flash. So that's actually pretty amazing. And what this is going to do is maximize not just the utilization rates of your NVMe, but also of your CPU resources, including GPUs. And with that, I will now hand it over to Joel.
All right, thanks a lot. Joel, yeah, you should, let me make sure you've got control here real quick. It looks like you do. Oh, wait, I think Josh has still got my screen. Hold on 1 second. Okay, let me pass it to you quick, and we should be ready to go.
Let's see if I can make this move.
There we go. Should be yours.
All right. Thanks, everyone, for joining. My name is Joel Diedrich. I'm with Kioxia, a world-famous brand name, formerly Toshiba Memory. I want to talk about networked NVMe flash at scale, and I've emphasized the word scale here. Our focus is on very large-scale deployments of networked flash as opposed to kind of the small silos that you often see in the enterprise. We are a data center-focused product, and I want to have a little fun with this and talk about some of the mistakes you can make, basically how to do this wrong, and then by inference we'll figure out how to do it right. So what is Kumo scale? First of all, Kumo is a Japanese word that means both cloud and spider, therefore the cloudy spider web logo. Kumo scale is a software-only product that implements networked block storage using NVMe over fabrics. And as I said, we target mid to large scale on-premise clouds, which means usually either service providers or people who are delivering something over the web or through your phone and have a need to build their own infrastructure because of the unique requirements of their applications. And that could be massive gaming, marketplaces, anything that has demand crashes. And we have built an architecture that's very focused on the cloud. And by cloud, I mean specifically orchestrated environments as opposed to permanently provisioned silos. And so, let's see if I can make this move forward here. So scale, as I said, means something north of 50,000 compute nodes, usually, almost always multiple physical data centers, multiple availability zones. And that brings some unique challenges. Basically, humans can't be very involved in the deployment and maintenance of each individual unit. Human in the loop doesn't work when you're trying to deploy 1,000 of something, nor does it work when things break. So automation becomes a focus to a far greater extent than it is in the enterprise. And your neighbors may be malicious. We talk about noisy neighbors a lot, but there are neighbors that want your data in the cloud, and you need to protect against that. So how to do it wrong? One is to neglect the media management aspect of networked flash. Flash today is sort of homogeneous. We all have so-called TLC, or the three-layer cell, three-level cell flash. But flash is about to explode into a variety of kind of a lush set of different flavors, including low latency flash, which is a kind of back to the future. We're going back to single layer cell, single level cell, and very small word lines and bit lines to get very low latency. TLC, of course, but QLC is going the other direction, higher density but lower performance and lower endurance, and people are even talking about 5 bits per cell now. And so when you think about deploying flash at scale, how do you deal with that diversity of behavior? How do you make sure the right data gets on the right flash? Especially when doing it wrong has a high cost. I mean, you can wear out QLC in a matter of months if you put the wrong workload on it, and you can blow a lot of money buying too much expensive low latency NAND. And so in an automated way, getting the right data on the right flash becomes mandatory if you're doing it at scale. And so don't ignore that. Another one, how do you deploy 1,000 storage nodes? You really need to think about zero-touch deployment. You can't have anyone clicking a mouse or even really writing scripts where there's any dependence on the physical location or characteristics of each individual node when you deploy at scale. You need to be able to take a cold machine, plug it in, fire it up, and it needs to find its place in the world, download the right version of the software, install itself, and get up and running without any help. And similarly with upgrades, and that, you know, making complicated things appear to be simple, as we know from the iPhone experience, takes a lot of work. And this is no exception. There's a lot of work associated with taking a product that works very well at small scale and making it installable at large scale. And then along those same lines, a mistake that would be easy to make is to neglect topology awareness. You know, at scale, as we know, things break. We all have to protect against SSD failure, but that's really just table stakes at this point. How do you handle a rack being partitioned or a row of racks being partitioned from the network? The public cloud guys, the first-tier public cloud guys have handled this at great expense. I mean, they've invented solutions analogous to Kumo scale and deployed them. But for the next tier, you really need to be able to handle an entire failure zone or an entire building going down, and how do you do that? So awareness of failure zone topology is a must, and your system needs to be able to partition replicas and distribute data in a way that is resistant to the failure nodes, the failure modes that are unique to your environment. And then finally, fail to disaggregate. I mean, as Josh said, the SSD vendors have a bit of an innovator's dilemma. We make products that are way too good for their application. They're too big, too dense, too fast, and too expensive to put one in every compute node. And the sweet spot capacity is in the background growing pretty rapidly. You know, we now are probably at the 4 to 8 terabyte neighborhood is kind of where flash is really efficient, but that number is going up, you know, with some pace, and I think 16 and 32 terabytes are right around the corner, and the design guys in the same building with me are thinking about 128 terabyte drives. So the appetite of application instances that can run on a single node is not growing anywhere near that fast. And so we're simply going to have to share these things. Direct attached, what was called SOFS for this webinar, has some hidden risks. It's very hard to do network planning when you don't know ahead of time which data is going to go where. A client NIC can be a bottleneck that you can't plan for if 1,000 compute nodes suddenly need the data that happens to be located on one client node. And when when IO, on the other hand, when you blend IO streams from many, many different applications, you get kind of regression to the mean. The chances that they're all going to be in a worst case IO storm at the same time are very, very low. And so, you know, the kind of law of large numbers works for you if you disaggregate storage. The other thing, you can't pay as you grow. I mean, for data centers, our customers are often in a very rapid growth part of their corporate lives, and if you buy your flash direct attached to your compute nodes, you tend to have to decide up front how much you're going to need for the lifespan of this computer, and buy it all up front. Whereas if you can buy storage nodes that are disaggregated, you can buy them half empty and just plug additional drives in as needed, which over time, the cost of money is not insignificant and can have a pretty big effect on overall blended IT cost. So just remember the law of direct attached flash. No matter what size drive you bought, it's wrong. And so finally, how to do it wrong, number 5, is to underestimate the power of orchestration. Orchestration means that a computer is deciding what runs where and not a human or a script. And the orchestration framework war lasted about 3 minutes, and Kubernetes basically won. I think any solution that lacks a really seamless, really deep integration with Kubernetes is just not going to age very well. The days of sort of static or scripted assignment of work to machines and therefore assignment of storage to machines is what I call a dead man walking. I mean, there's still a lot of it around, but it's not going to last. And so, how to do it right? Choose a disaggregated solution that's designed from the ground up for large-scale deployment, where the provider has put in the hard work necessary to make deployment fully automated and fully integrated with orchestration, and choose one provided by a vendor who understands flash media profoundly, including the coming kind of diversity of types, and has the stamina to build and support a solution. As Ronnie said, trust but verify. So that's the end of my prepared talk. I guess we'll move now to a panel.
Absolutely. Thanks again, Joel. So since we're running a little behind, guys, I'd like to ask you each limit your answers to about a minute or so. So the first question is, when it comes to planning NVMe over Fabric deployments, what are the top 3 factors that companies should consider? We'll start with Rob Davis and Mellanox.
Sure. So first of all, performance of the network. You've got SSDs that can provide today 20 gigabits of performance, and by next year, probably, at least a third more, maybe twice as much. And latency is under 10 microseconds, so you need a network that can support that. Secondly, applications that can take advantage of that performance. For example, if you look at applications designed around hard drives, I'll take Ceph as an example. It's used a lot, right? You put SSDs in it, the performance really doesn't go up much. But if you look at the applications, NVMe-mesh and scale that were talked about here, they're designed for NVMe. SPDK was also talked about here, designed for flash. These are the kind of applications you want to make sure you're designing around your NVMe over Fabrics deployment. And then thirdly, experience. The lab that WDC talked about, Mellanox, who's been, I think we demonstrated our first NVMe over Fabrics pre-standard versions back in 2014, and we're actually working on it before that. Many of the companies on this call have been doing NVMe over Fabrics for a long, long time. And then there's others that have come in that weren't interested in the high performance space because there was no SSDs, no NVMe over Fabrics. So it wasn't a volume market, that are now coming into the space. They don't have the kind of experience that the companies that have been in it all along have to do the complicated things that have been discussed on this call.
Excellent. Thanks, Rob. Tom, do you have anything to add to that? Factors you see?
Obviously similar stuff. So I would say start with what infrastructure is already in place. So there's a lot of TCP networks out there. Do you need to re-engineer your network, put new equipment in to support things like, say, Fiber Channel or Rocky or InfiniBand? If all you have is TCP, that's something to consider. Also, what are the applications that are running on the network? What are they written to? If most applications that run on the compute nodes are running TCP, there are some exceptions to that, because then you're looking at modifying the actual applications if you're going to run it over different transports. And then the ease of the deployment, what's the easiest to deploy? So I always like to do the comparison of Betamax to VHS or IP to ATM. One technology may be better, but the other one might be good enough and easier to use. That's my 2 cents.
Very good point. Dave, what do you think from Western Digital's perspective? How do you see this?
I completely agree with what my colleagues have said. My first point would be, don't underestimate what your applications need and don't need. So have someone in your organization really understand the storage capacity and performance of the various workloads and the cyclical nature of them. Otherwise, you're going to, as we all know, end up with a bunch of siloed, expensive flash not getting used. The other is understand the infrastructure, as everyone has said. Make sure there's enough bandwidth, because obviously, even with SSDs in servers, all you're doing is moving the bottleneck around. So really understand what your application workloads are. And then the third one really would be just get started. Come up with a sandbox in your organization, and a small high-speed network, some flash, some NVMe or Fabric, and then start kicking the tires on it. I mean, Western Digital came up with a lab to sort of accelerate that, but whether you use our lab or come up with your own sandbox, but get your hands dirty on it and see where it could benefit your specific environment. So that's really it.
Yeah, I think that point about chasing the bandwidth limitations is a good one, right? 5 years ago it was storage, now it's maybe networking or maybe in the server. What do you guys see, Josh, on this side?
I think what has been said so far is absolutely dead on. I do take issue, though, with one idea here that is promoted, just talked about by Xilinx and by some competitors, is that I think the value of TCP is in the knowledge and comfort level that exists in a lot of organizations, not in the network itself. What I mean by that is, and this was touched on also by Western Digital, if you think you're going to just start putting NVMe on your existing TCP network, I think 99% of people will be sorely disappointed and have a terrible experience. The reason for that is there's been no need to profile until now the I/O that's going on local NVMe. And suddenly you're going to take what was on a local PCIe bus inside a server and put it out onto your network, which means you could be more than doubling your network traffic. And what's more is what used to be a localized activity on an individual server will now burst and affect the network and possibly affect other systems in a very unpredictable fashion. And as we saw, if you give TCP an unpredictable load and push it near its limits, you're going to get very, very high tail latencies. So you're going to take what was an extremely high performance local device, and with TCP, you could potentially be affecting other systems and get very high tail latencies where before you had consistent performance. So I'd really caution folks, not against using TCP, but caution them on thinking that you're just going to take your existing TCP network and move NVMe on top of it. I think everyone, TCP or Rocky bound, is going to need to deploy a new, at least set of switches and possibly interfaces to have the bandwidth necessary and keep the latency under control.
Yeah, I think certainly this concept of running on a converged network, whether it's TCP or Rocky or whatever, this is something for most storage people we haven't done for 25 or 30 years, or at least 20 years. So it definitely brings up new issues that you have to worry about, no doubt about that. Joel, what are you guys thinking from Kioxia? What do you guys see?
Well, we've actually had fairly good experiences with running over existing TCP networks at pretty reasonable scale. Back to the characteristics of applications and their I/O intensity. 10,000 IOPS per terabyte is a fairly storage busy application. I mean, there are a few cases that are significantly above that, but that's not an unreasonable kind of upper middle bound. And so you think about what does that mean to my network? Well, 50,000 4K IOPS is 1.6 gigabits per second. So even 10 gigabit networks, you're using 15% of it for a very, very I/O intensive application. Now, that said, what you really want, I mean, the bandwidth and IOPS these days are less of an issue than latency, of course. And what you want, if you want low latency, is big pipes that are mostly empty. I mean, nobody cares about the commute lane if the freeway doesn't have any cars on it. And so you don't want to plan for full networks. But I think there's a little bit of fear of the dark, that's maybe to an unnecessary extent around running over TCP and over existing networks. We find it actually works pretty well. The other thing that hasn't been mentioned that I think is a consideration that you really need to pay attention to if you're considering your first NVMe over Fabrics deployment is which version of which distro of Linux you're running. The NVMe over Fabrics drivers with RDMA were first present in the upstream in the kernel 4.8 and TCP drivers in 5.0, and so synchronizing with with your favorite Linux distribution is kind of an important variable in making sure that the drivers you need are in box.
Excellent. Thank you very much. So with that, we've got, let's go to our first panel question. I'll launch that here, or the first poll. And that is, what experience does your organization have with NVMe over Fabric? It's multiple choice, select all that apply. We'll give that a couple minutes, and while that runs, we'll go to the second panel question, which will kick off with Western Digital. And that question is, NVMe over Fabric has significantly better performance than SCSI-based storage networking protocols. When retrofitting existing storage networks with NVMe over Fabric, what are some of the bottlenecks that might be encountered that could impact these performance gains? And Dave, we'll start with you on that.
Oh boy, it's a pretty broad topic. I think in general, again, if you're retrofitting NVMe over Fabric over existing storage infrastructure, prior to doing it, you'd better make sure that there's, as Joel said a minute ago, that all lanes of the freeway are empty, and if they were full, they would have adequate capacity. So it really is understanding what the maximum possible workload is of your existing infrastructure, and how will that change if you now have a bunch of NVMe over Fabric traffic and applications hammering it. So I can't really say where do you start. It's more really understand what you've got available, and will it hold up under not even a worst case workload, but like, let's say, a relatively high performance workload at peak. And so start there. And again, it gets back to the point that lots of us have made. Understand what your workloads need for application and storage performance. And then if you've got multiple ones of those firing off at the same time, will you be in trouble?
Excellent. Josh, obviously you guys at Accelero have done a lot of, I'll call it retrofitting of existing networks, whether it's standing up new ones or not. What have you guys seen as kind of issues that impacted performance?
I think I actually ended up touching on it on the previous question, which is that it's what you don't know that bites you. It's not what you know. So in our experience with a lot of the customers, they do not have empty lanes. I don't know any web scaler who retrofits their network to 25 gigabit because they were only using a gigabit of traffic. So they're very tight on money. So what we tend to find is infrastructures that are large scale out infrastructures and standardized, or at least normalized, are close to their network bandwidths, especially within their acceptable latencies. So this goes back to, if you're going to retrofit an existing network for NVMe over Fabric, you have to be able to profile your applications. You have to know the loads that they're putting on what is probably local storage. And furthermore, if you're thinking about moving to NVMe over Fabric, you have some serious decisions to make that while traffic can span multiple racks or even an entire data center, you have to think about failure domains, where you want your traffic to go. And if you have to improve your east-west connectivity in your switching layer, rather than just your north-south, or keeping it within the rack. So long story short, profile your applications, know how much you're actually using, and know your existing utilization of your network before you're going to retrofit.
Yep, certainly a knowledge is your friend sort of situation here. Joel, what do you guys recommend at Kioxia?
Well, an additional factor beyond networking, which everyone's been pounding on, is is to understand how work gets mapped to flash. You know, a network latency of a millisecond or two in many systems would be considered pretty bad. But if a read lands on a flash chip that is busy doing an erase, it's going to wait for 3 milliseconds or more. And so an optimal mapping of application to drive and an optimal management of the low-level media turns out to affect the latency distribution as much as the network design. And so a system that's designed to characterize each workload by storage class and figure out how to map it to individual flash, individual SSDs in such a way as to minimize latency outliers can have a really large effect. And so there's you know, multiple layers to this, as with anything. I think what we've seen over the last 10 years or so in hyperscale is that the spending on network cross-sectional bandwidth has far exceeded the spending on any other segment of the data center. We went from highly oversubscribed kind of Christmas tree shaped network to CLO networks that have kind of constant cross-sectional bandwidth. And that was to the benefit of the networking guys. I mean, if you're selling NICs or switches, you made a lot of money over the last 10 years. But the reason they spent that money is that keeping latency low means keeping the freeway mostly empty, and it's worth the money.
Absolutely. Rob, you probably have a few things to add to that one too, I'm sure, being a network vendor. I think you're on mute, Rob.
Yeah, I was, sorry. I'd say if you're getting ready to deploy NVMe over Fabrics is to make sure you have a partnership between the storage team and the network teams at the customer in your environment. Because what you'll find is that the storage team has this new high performance NVMe over Fabric all flash array and servers ready to connect to it, but the network team doesn't know that this is going to happen or isn't bought into it or whatever. And then you end up having a lot of trouble getting the network set up to work correctly with the bandwidth and latency requirements you need. So make sure the network team is bought in and is part of the planning so that the network is ready to go when you turn on the NVMe over Fabric solution.
Very, very good points. Tom, you want to add anything to this one?
Yeah, I'll throw one piece in there that when you're looking at storage appliances and you're looking at NVMe-oF, make sure it's native NVMe-oF. What I mean by that is, if let's say you're running an iSCSI network and you're comfortable with iSCSI and you decide you want to use an all-flash array that's based on iSCSI, where they're doing a protocol conversion, you're not going to get anywhere near the performance. And I illustrated that earlier in the performance slides. So I would say be sure as you're starting to map out your solution that you're looking at, it doesn't matter which transport protocol so much as it is that you're running native. If you really want to get close to that direct attached storage performance. And then I would comment back from the previous question and combine with this question. I would agree with Josh that you better understand that network. If you're running disaggregated or distributed storage, the east-west traffic is going to go up, and whether it's a whole lot or whether it's a little or somewhere in between, that's something you better understand. So you are, let's say, either retrofitting or designing the network to support that load of traffic.
Absolutely. And with that, let's kick off our final poll question. This is, which classes of NVMe over Fabric use cases have your organization evaluated? This is, again, it's multiple choice, pick all that apply. And while we let that question go ahead and get answered by the audience, we'll go to panel question number 3, and that is that 2019 marked the year that every large storage array vendor supported NVMe over Fabric across their product lines. What other enablers are needed for NVMe over Fabric to be widely utilized in production storage networks? And that's regardless of whether it's scale-out flash, array-based, or otherwise. And we'll start with Joel from Kioxia for this one.
Yeah, I think the large storage arrays serve a market segment that's quite different in a variety of ways from the sort of cloud and data center market that at least we're focused on. Back in prior life, I was involved in network interface semiconductors, and we would say, "Hooray, we got designed in at Cisco," but then you stand back and realize they offer every interface available, and they don't have a dog in the fight on which one wins. They're just going to sell them all. And to some extent, array vendors are like that. They need to offer every interface that a customer may want to use, and maybe a little bit agnostic about which one the customer chooses, as long as they pick my array. So I don't view that as a vote of confidence for NVMe over Fabrics, or the contrary. I think the tectonic plate movement here is that NVMe is going to displace SCSI as the default way to talk to block devices, and SCSI will be moved off into the special case of rotating storage. And NVMe over Fabrics is the canonical transport for what is now going to be the standard way to talk to block devices. So you're going to see it everywhere. The adoption of NVMe over Fabric, I think, is going to be extraordinarily rapid because it talks to the new device, which is the sort of mainstream way to store bits, and that's TLC flash.
It's a really good point. Rob, what do you think?
I agree 100% with that. As far as one other thing to add about the mainstream enterprise suppliers is that internal to their high-end machines, they're all using NVMe, or many of them have announced that they're using NVMe over Fabrics as well. So one of the use cases that Mike, you brought out initially is inside a lot of those systems. I think Pure Storage actually has blogs on it, their architecture. And, the others maybe aren't so open on it, but I think you can guess that there's a lot of NVMe over Fabrics internal in those back-end networks. So there's a kind of a vote of confidence from those guys on this new technology. As far as enablers or things to get this moving even faster, I think the announcement that I think there's announcements out of VMware that they're supporting it. I know there's now third-party Windows drivers that are starting to become available for it. These are enablers. Linux has always been very early and is very supportive from inbox perspective in the space from a driver side. Software that supports it across multiple different ecosystems would be something that would accelerate it even faster. But I agree that this is something, because it's native on the drives and it fits nicely into network at a very low latency, high bandwidth capability, that it's going to really take off fast.
Absolutely. Tom, what do you guys see?
In order to really make this move well in the market, and I believe it was Joel that brought this up earlier, I think as the Linux solutions for the NVMe-oF are not only pushed upstream, but they're also adopted by the Linux distributions and made available in the distributions, in distro. And that's happening, but as that becomes ubiquitous, I think that's going to make it even easier for customers to accept it and deploy it.
Excellent. And Dave, what do you think from Western Digital's perspective on enablers to help NVMe over Fabric take off more?
I think everybody ahead of me's covered it, to be blunt. I think particularly Joel in his comments about most large array vendors are sort of one size fits all. So I think you need to be careful. Not that their products won't perform well, but it just in terms of really understanding what the access required is. And I think, I think all the comments made are right on the money. So I can't, other than, sound like a broken record, other than really understanding your IO traffic and peaks and valleys of it, that's probably, one of the first steps you need to do.
Excellent. Josh, obviously you guys have done a lot of fielding of NVMe over fabric-based storage networks. What have you seen as the biggest thing that's helped get people over at home?
I think the thing that's lacking a bit is really at the management and administration level, to tell you the truth. We're getting it down, as was evidenced and said by my previous colleagues here on the call, that even large array vendors are using NVMe over Fabric on their back end. And that's actually telling. They've recognized the value of disaggregation of the media so that they can scale their front end and the back end independently, but they're doing it in a very controlled way. And if you look at really where we are with NVMe over Fabric, it was largely driven by the world's hyperscalers, because they already, in extremely large deployments, know how to manage thousands of individual drives, or splitting those drives into namespaces, thousands or tens of thousands of namespaces. They architect their exact application to the specifications that they need to manage that. But now when you look at us mere mortals who are looking at adopting NVMe over Fabric, what would you do if I just plopped down 100 or 1,000 network individual 4 terabyte devices on your network? We've talked a lot about iSCSI. Think about it. Drives have been SCSI protocol forever. And when iSCSI came out, there wasn't this notion that you're just going to share individual drives over iSCSI. No one said we're going to deploy hundreds or thousands of drives, and each one is going to be available individually. iSCSI was the protocol that encapsulated SCSI on the network, but it went through a controller. But we've seen with NVMe that controller now represents a bottleneck. So you have to have a way to have all these individual drives, but manage them as a whole, and give yourselves a system that gets the performance of NVMe over Fabric, doesn't sacrifice that to do management or central controller bottlenecks. And you can do that with some products such as Mellanox's SoCs. Those pair very nicely and are very lightweight. There are other solutions coming, and Western Digital, of course, has their solutions as well in their flash. I guess you call them JBOBs, or bunch of flash. So we're moving that direction. The challenge will be to manage that, actually manage and administer in a way that's useful.
Very good. So guys, we have one Q&A question. That Q&A question, and we'll start with the network guys first, so Rob and Tom. The question is, we've touched on TCP versus RDMA transports, but are there any fundamental strengths or applications where Rocky versus iWarp differentiate themselves? And I guess there's a bigger question is, and granted, we don't have any iWarp people on the phone necessarily, but is iWarp still alive, or is it a zombie? Rob, why don't we start with you on that one?
Sure. So I think NVMe over TCP was kind of a nail in the coffin to iWarp, because what iWarp, its differentiation from Rocky was that it supported, it ran over TCP, and it had more latency than Rocky, so it was very similar to NVMe over TCP, and NVMe over TCP doesn't require, goes through the standard stack sockets interface. So to me, that was one thing that sort of has pushed iWarp to the side. And then the second is when Intel recently has a new line, or announced Rocky support across their NIC product line. So I think, they were one of the big supporters of iWarp, and now that they've moved to Rocky, there's public announcements by a couple of different large hyperscalers that they're using Rocky. Many of the others are very secretive, but you can draw your own conclusions. I think iWarp is sort of, as someone earlier said, VHS and beta. I think it maybe is falling into the beta area.
Very, very good point. Tom, what do you think?
Well, the other thing you have to look at, I agree with Rob's assessment, is if you're going to have performant iWarp, the actual NIC controller, the endpoint, has to terminate TCP on chip. And out of the 6 suppliers, there are only 2 that are capable of doing that anymore. And the bigger ones are not. So that plus the fact that, I mean, iWork runs on TCP, why not just run TCP? I look at it like that. So I think just the ecosystem alone is going to be an impediment. And then for the points that Rob pointed out, I think as well are pretty valid.
Excellent. Well, thanks everybody. Again, we will send out the recording to the webinar and probably on Thursday, along with a copy of the slides in PDF format. And everybody have a great holiday, and we'll talk to you next year. Thanks much.